Hello and welcome to today's lesson on cooling graphs. Today we will explore the stages of condensing and freezing by graphing energy and temperature. We previously looked at heating graphs. We learned how the temperature of a substance changes as it is heated and the transitions it undergoes between different states. As with our lesson on heating graphs, we begin with a graph with energy in joules on the x-axis and temperature in Celsius on the y-axis. We will be plotting what happens as steam turns to ice. At the beginning of the cooling process, our substance is in the gas phase. Imagine a saucepan of water that has been boiling and then taken off the heat. The steam represents the gas. As the gas cools, it loses heat energy to its surroundings. This heat loss reduces the kinetic energy of the gas particles, causing a decrease in temperature. Initially, the rate of temperature decrease may be relatively rapid. This is because a significant temperature difference exists between the hot gas and its cooler surroundings. However, as the gas cools and its temperature starts approaching that of its surroundings, the rate of cooling slows down. Hence, on a cooling graph, instead of seeing a straight line, you will observe a gently sloping curve. As the gas continues to cool, it eventually reaches its condensation point. At this stage, the temperature of the gas stops decreasing. Instead, the gas undergoes a phase change into a liquid. This process is known as condensation. During condensation, the energy removed from the system goes into overcoming the intermolecular forces of attraction that keep the particles in the gaseous phase. Since this energy is used for the phase change rather than lowering the temperature remains constant on the cooling graph until all the gas has turned into a liquid. Once all the gas has condensed into a liquid, the cooling process continues. The liquid now starts to lose heat energy, causing a drop in its temperature. During this stage, as the heat energy is removed from the liquid, the kinetic energy of its particles decreases. This decrease in kinetic energy makes them move slower, leading to a temperature fall. Initially, this cooling might be rapid due to the temperature difference between the hot liquid and its surroundings. But similar to the cooling gas phase, as the liquid's temperature nears that of its surroundings, the cooling rate slows down. This creates another gently sloping curve on the cooling graph. Eventually, the liquid cools down to its freezing point. At the freezing point, the liquid undergoes another phase transition, this time freezing into a solid. Just as with condensation, the temperature remains constant during this phase change. During the transition from liquid to solid, the heat energy removed from the system goes into forming the strong intermolecular bonds that hold the particles together in a solid structure. This means the temperature will not change until the entire liquid has frozen. So, on the cooling graph, you will see a flat line representing the constant temperature. Once the liquid has fully transitioned into a solid, the temperature begins to fall again. In this stage, as heat energy is continuously removed, the kinetic energy of the solid particles decreases. These particles vibrate less vigorously as a result. The temperature keeps falling until the solid eventually equilibrates with the temperature of its surroundings. Like in the previous stages, the cooling might start relatively quickly but will slow down as the temperature difference decreases, resulting in a gently sloping curve on the cooling graph. Today we have looked at the process of cooling, plotting it on a graph. Understanding these stages allows us to recognize and explain the different phases and transitions a substance undergoes while cooling, enriching our knowledge of energy transfer and state changes.